Hey, welcome back for part 2. In the previous video, we went over the general concepts behind how we solve the n-queens problem using a search algorithm, and we implemented a serialized function to allow us to return our internal types in the correct format following inside-out TDD. So sort of planning out how this algorithm is going to work and then implementing the individual components that we need to complete the whole thing. And in this session, we will go through creating the validity function to actually prove whether or not a given board is a valid one, to check for all the diagonals and whatnot, that the queens aren't touching each other. And then we're going to actually implement the search algorithm, which is going to be really, really cool. That's going to tie everything together and make it actually work. So we can serialize. That's really cool. The other thing we need to do is to check if something is valid. So given a board, which is not necessarily a complete board, then we want to test whether it's valid. So this is, these things we've highlighted here in red, these boards that cannot be complete solutions because they include adjacent or diagonal queens. How do you programmatically recognize which ones of these are the red boards, the invalid ones that can't be genuine solutions? So let's say fn is valid. There is valid board, and the boards look like that, and we're just going to turn a bool and unimplemented for now. Okay, and let's do the same as before. Move this to a different file. Hang on. There we go. Validity. Okay. So let's get some tests for this. Starting with something dead simple. What would be a dead simple test? I guess do the same as we did before and start with a single cell. Single cell is just a queen. So single tile, I should really call it, not cell. Single tile board is valid. And there's really no way for it not to be valid because there's no other queens for it to interact with. So this would be let board equal vecbang option, oh sorry, not option, sum 0. And that's all you'd have. And then what to pass it into is valid board, and assert equal result should be true. Boom. And that fails, obviously, and it fails in the way that we would expect, which is always important to check. Now, to pass this, well, let's start by returning true, simple as valid board for single tile. Let's say implement validity for single tile. And then let's go with a 4x4, following the same pattern we did before. We're also going to need to check incomplete boards, but let's just start with a complete board. Or arguably, actually, no, I tell you what. What's probably better is instead of going by boards and board sizes and things like that, let's go by the behaviors that we're actually checking for and how the queen acts. So, for example, 2 queens horizontally next to each other is invalid. We could write a test to check for that. We can't do a test to check for vertical queens because our fundamental data structure prevents that from ever being possible. But we can also do ones for diagonals. So let's say, given two adjacent queens, so I guess we don't need two there, it's kind of obvious, should return invalid. Or, yeah, should return invalid. And let board equals vecbang. So this is going to be, let's make it a 4-based sort of board. Like if we take this one, for example, and we modify this in a way that it will be invalid for an adjacent queen. I think that's correct, isn't it? Neither of them are... Yeah, there's no diagonal in problems here. There's just the fact that two of them are next to each other. Okay, so let's try that then. Let's try, say, 1 3 0 0 1 3 0 0, and this time we want it to be false. Okay, so how are we actually going to check that? Let's start with let result equals true, return result. Now at least the first one will consistently pass. At the end of semicolon. And we want to check whether there are no adjacent pieces. Really interesting part of this might be a bit confusing to begin with. It'll make more sense when we write the search algorithm. Really interesting part of this is that we can optimize it by only checking for the most recently added piece of the board. We don't actually want or need to check every piece on the board. We only want to check the most recently added queen because all the previous ones have already been checked for validity when they were initially created, right? If you think about the algorithm we were talking about earlier, in order for these to turn up red, and then in order for us to know not to explore these further, we have to check them for validity. In which case, if we already know that that this board is invalid with these two pieces, we don't need to check those two pieces again. So when we get to this point and we're checking this for validity, we only need to check this column, right? We just need to check this one's relationship to these two, and we don't need to check that one's relationship to that one. So what we can do is we're going to need to know how many valid pieces there are, or how many pieces have been placed on the board, like how far through we are. Actually, I tell you what, because we're starting with everything completed, let's ignore that. And let's just say get the full length of the board and just assume that everything is complete for now. That simplifies the problem. We can update it with another test driving at that feature later. So if we assume the board is always complete and the board is of size n, then we want to take the most recently added queen, which will always be the last one. So that's going to be newest queen position equal board n minus 1, because it'll need to be 0 indexed. Newest queen position, and then for this newest queen position, we need to check whether or not it conflicts with anything else adjacent to it. So we can say for that's even for y in 0 to n. For y in 0 to n, check to see if board y Is that right? Yeah. Yeah, that's right. Check to see if board Y is equal to newest queen position. So if that is true, then result equals false, and we can break out early. And result needs to be mutable. Okay, that's not quite worked. Why is that? So we're saying for Y until N, so that's going to go 0, 1, 2, 3. We take... oh, hang on. No, look at the test name that's failed. Single tile board is valid. Okay, so actually we've passed our new test. We've broken the previous test. So why doesn't it like a single board in this position? Probably because it's always going to be true, isn't it? If you have a single board, you're going to enter, yeah, that n is going to be 1. So you're gonna go into this loop once, and you're going to say if board 0, which is always going to be this value 0, is equal to newest queen position, which is also 0, then the result is false. It doesn't work for a single-sized board. Oh, what a pain. How can we fix that? If board Y equal to newest queen position, 0 to end. It would be nice if it just didn't enter this at all in that scenario, right? That would probably be ideal if there was a way to change this condition to just not enter when we're looking at a board size of 1. The challenging thing with these edge cases is always to try to find a neat way of handling them without letting this edge case completely change the whole structure of your function, which then makes it harder to read, and developers are looking at your function, spending most of their time reading code that has almost nothing to do with the actual main purpose of a function. That's just managing edge cases, right? But I might end up having to do that. We'll see. For each row in 0 to n. Okay. So think about it this way. When we first create the frontier, right? When we first populate our search function, we create 4 entries and all of them are valid. There's actually no way, I mean, we wouldn't create an invalid one off the bat, would we? But because there's only 1 queen to begin with, there's nothing else it can conflict with, so it's never invalid. So that means that we can always assume a one-sized board is valid. We don't actually need to do any validity test on it. So just do that. So that basically is telling us to just ignore any one-sized boards, and it passes our test. And it's always going to be true because I'm saying that wrong. I'm saying one-sized boards, but it can also mean well, I'm kind of planning to change the meaning of n later. So right now n is full size of a board, but eventually this will loop not to the full size of a board, but just up until wherever the latest queen is. So up until the point where we need to test the queens for validity. That might be a little bit confusing. Hopefully it's not, but I won't worry about it. You're about to see how all that works. So cool. Implement adjacent queen check. Now, there's nothing really else to do with the adjacent queens. Oh no, there is one other thing actually. Yeah, there's one other scenario you can check for, which is what if they are far away, right? What if there is a an adjacency hit, but it's, you know, these two are right next to each other. What if it's really far away? I'm pretty sure that'll work fine with our test, but I just want to be sure. How can we do that? How can we create a test case for that without also causing a diagonal hit? How can we create an isolated test of that? I think the short answer might be that we can't. I'm not seeing an easy way of doing it without also causing other problems. Because anywhere where you can move these queens, where they're adjacent to another queen, but more than one tile away, is also going to cause it to be in a diagonal conflict with another queen, in which case your test is not isolated, you're testing multiple things. I think a neater way to do this might be to start testing incomplete boards, because we can definitely do it then. So for example, it'd be nice to put this here, but we can't because this queen is in the way. But what if we just get rid of that queen? Then we're testing an incomplete board. So that would be, just put n for none there. That would be 130 none. And we could call that given adjacent queens on income, given far adjacent, as in more than one tile adjacent, far adjacent queens on incomplete board should return invalid. Okay, and that's going to... I'm being a bit lazy with the tests here, with duplication. Worth noting that probably it would be worth... writing a short macro or using one of the libraries that can do it for you to actually turn these into parameterized tests, because every test here is the same, really, isn't it? But for the sake of simplicity and time, let's just copy them for now and live with the duplication. Okay, so we've created that test. Creating a board looks like this: 131n. So 131 none. And we're saying, is this board valid? And we're expecting false. And actually, it's passing right away. So that was pretty easy. Interesting. This raises an interesting question, because how can I demonstrate newest queen position? Oh, I see. Oh, that's interesting. Because we didn't unwrap this, we're just comparing the options, and actually, because they're both options, it's happy to do that. So, sorry, caught my microphone there. That's really neat. It's also non-optimal though. It's non-optimal for reasons. It's non-optimal because it's basically checking things it doesn't need to check. So it's going to get to here and it's going to say, oh, does this match this? But actually there is nothing there to check. It also won't work with diagonals. Yeah, I'm pretty sure using this approach will cause problems with diagonals. And what we should really do is unwrap that into a usize. And that will presumably cause problems here. Yep. But I think the right thing to do is to ensure that this can always be unwrapped, right? So if we unwrap this now, it's going to cause an error in our case because we've got this none here. It's going to get to there, try to unwrap it, and then fail. But actually, we already know we don't need to look at that, or we can already easily figure that out anyway. And we don't need to iterate that far into the problem to begin with. We just need to know how far through this incomplete board is, which we can do by replacing n. Is n used anywhere else? It's used here. That's fine, I think. Yeah, that's okay. We can do that by saying board dot We can iterate it. Yeah, let's iterate it. And oops. It's a filter. So that's going to give us a row, right? Or no, sorry, a column, not a row. And if it's a column, well, an optional column, and we're going to want to filter only to the ones that are there, that aren't none. And then we're just going to want to count, and that is going to give us the number of complete rows, you might say. Yeah, number of complete columns. And this newest queen position, I might specify that's the Y position, or the, I suppose, yeah. I'm realizing I might have gotten some of my variable names wrong before, actually, but too late now. Yeah, so if you think about it, the value that we're getting back out of this board variable is the Y position of the queen. So we're saying, okay, and that should actually be X, really. So, yeah, because we're going along like that, yeah. So this X value for the board, unwrap it and check that it looks valid to this. We can always unwrap this because we've done this check here, so we know how many of these are sums and not nones. This does have one assumption baked into it. It assumes that there are no nones mixed inside the sums. I think that's fine though. If you were doing, a serious library you're expecting other people to use, then you should probably specify that invariant in a comment above a function, making it clear that there's an invariant baked into this function you need to observe. In this case, no, let's skip over that. So this is implement valid func for incomplete boards. Okay, so even if a board isn't complete, it'll now work with our invalid function, and we've also tested that it works for queens that are more than one tile adjacent. Now let's try diagonals. Given diagonal, let's say diagonally adjacent. Yeah, I guess, is that? Let's redefine some of these ones. Given far horizontally adjacent, given horizontally adjacent, given diagonally adjacent queens should return invalid. Invalid. Now let board equals vecbang, and we can need a test case. So let's say now what we can do in complete boards, we can create test cases much more easily. So we can just do that, right? And that's 0, 1, easy. So that's sum 0, sum 1, none, none. And actually, trying to implement this is pretty simple. If you've done diagonal boundary checks before, you only need to do it once, and I've done it a lot on my chess engine, and it's pretty simple to do once you have a hang of it. Hang on, why is that passing? 0, 1, none, none. And it's already passing. It's already coming back as invalid. Ah, I know why. And I know how we can use a test to catch that error and drive the solution. So I don't think we've had an actual, other than the single tile test, we haven't had an actual test that a board is valid, right? We haven't done that yet. And that's the test case we're missing that's resulting in this test passing that shouldn't be passing. So basically it's passing in scenarios where it shouldn't, or it's becoming false. So it's becoming invalid in cases where it shouldn't do. So given a given complete valid board should return valid. And in this case, we just want our complete solution here. So that's 1302. Let board equals vecbang sum1, sum3, sum0, sum2. Let result equals is valid board. Assert equal resultant board. No, sorry, what am I saying? Resultant true. Okay, so that should fail, I think. Yes, okay, it's failing. And the reason it's failing, I knew a minute ago, and I can't remember now. Why is it failing again? I think it's an off by one error, right? It's because because we're checking the newest queen position Y against itself. I think we're including the current queen who's just been added. So if you think this is a complete board, it has 4 items, that value is going to come back 4. So that's going to go through 1 to 4, which is going to be 0, 1, 2, 3. Because it'll, 1, 2, 3 actually, because it'll skip the first one. And this is the right side of a range in Rust is, what do you call it? Non-inclusive. So 4 won't be included. I'll just do 1, 2, 3. And that third one, 0 indexed, will be the final entry. So in other words, we should have a -1 there. And it's still failing. Drat. Why are we still failing? Assert failed, left equals right. Given her, oh, hang on, it's failing on a different test this time. That's exciting. Okay, so let me just check something. If we undo this and save, the test that's failing is given complete valid board. Yep, so the valid board fails. If we do that, the valid board now passes, but then one of the tests that we thought was passing before is now actually failing, and we've had to catch it by adding this test. Okay, that's quite exciting. So is it the far one? Yeah, far horizontally adjacent queen on incomplete board should return invalid. So this is going to have 3. This should have 3 as the number of incomplete columns. Let's just check that. Number of complete columns, not incomplete. It's a bit annoying that I have to type this out. IntelliSense doesn't yet quite understand interpolation in Rust. And I've typed it wrong. Okay. Yep, it's coming out as 3, so that value is coming out as we expect. Then it's going to give the position of the newest queen, which it's going to get as -1 to 0 index it. It's going to get 2, and it's going to say 0, 1, 2. The latest queen is at position 0. Then the idea is it should look at the other 2 queens and say, are either of you also at position 0? Are you horizontally adjacent? So it's going to loop through this and do 1 to 3, which is going to come out as 1 and 2. So it's only going to check 1 and 2. That's the problem, isn't it? 0, 1, 2. Hang on, wrong test. Yeah, wrong test. 0, 1, 2. It's going to include this one, which is one we don't want to check. It's confusing. Wait, no, hang on, no it isn't. No, because we've got the -1 here. So that's actually going to be 2. So it's going to be just 1. It's only going to check 1, or it should. Let's check. So only, so checking X. Checking 1, yeah. It only checks once, and it checks this field here. So it's basically going to be looking at that and saying, is 3 equal to 0? Which it isn't. So why is it then setting it to false? Hang on. Let's print the whole thing out. So checking X, I want to know if board X.unwrap is equal to newest queen position Y. Is 3 equal to 1? Okay. So there's no reason it would ever go into here then. Given far horizontally. Ah, right. Oh, yes. Okay. So it's failing because, as I was observing, it's checking these, right? It's not checking the first one. And actually, we intentionally created this to test whether it would work on tiles that were more than one space apart adjacent. And as part of that, we're checking one in the first column conflicting with one in the third column. We made that change earlier to skip past the first column, but I'm now realizing was a mistake. There must be a way to do that that works for single-sized. Well, we have to do that to pass this, but then that's going to break single tile. Oh, it didn't break single tile. It's valid. Doing the -1 at the end has fixed that problem for us for single tile boards. Oh, well, beautiful. There you go. Okay, that was a little bit messy, but we're getting there. So we kind of had a few things going on there, but the main thing is fix valid function for a complete board. Or let's say for valid board. So we got a little bit complex there. Just in case anyone's lost, what we did there was improve our validity function so that we can determine these not red boards, right? It was casting everything as red, and we just fixed it to recognize that some of them are not red. Now, the more interesting thing is diagonals. And like I was saying, diagonals are actually really simple to check for with a little trick. And the trick is basically this. If we take our test case for diagonals and think about this as, let's say we're looking for all diagonals of this tile here, then in terms of xy coordinates, this one to the left would be x plus 1, y plus 0, right? And then all the way through to x plus 3, y plus 0. And then down here, we'd have, x plus 0, y plus 1, and so forth until y plus 3. And the interesting pattern is that if you look at their diagonals, each one, the x and y values are the same, whereas they aren't for these, right? If you look at the in-between ones as well, here is 1, 2, and here is 2, 1, and so forth. The diagonals are unique because the difference in x and y is always the same. So it's dead easy to check for diagonals by doing what? We're going to need the position y and position x. Number of complete columns. The number of complete columns is the position x for the newest queen, essentially. So you can say diff. I thought there was an absdiff function or something like that, isn't there? It's a U size. Oh, I'm being silly. Sorry. I need to actually give this thing a name first before I assign it. And let's call this xdiff equals, here we go, absdiff with x, and let ydiff equal newest queen position y dot absdiff with y, which is this. In fact, can I just... There must be a way to do this. Control-Shift-V? No. Control-Alt-V? It'll be something like that, won't it? Ah, yeah, Control-Alt-V. Wait, there are two occurrences? Oh, yeah, of course. Well, we'll just delete the print line anyway. Okay, so we've got the y position out there. We've got the diffs of both. And if x diff is equal to y diff, then we know that it must be one of these here. We know that it's a diagonal. And in that case, we want result equals false and break. Oh, we've broken everything. Cool, that's always exciting. Let's check to see if... Okay, yeah. So without these changes, it's okay. With these changes, it breaks. And presumably, these haven't caused any... Nope, it's this part, okay. So what additional tests are we breaking? Given complete valid board should return valid, is now failing, and the diagonal one is still also failing. Interesting. I've done something wrong here. First things first, to start making some sense of this, let's improve this variable name. This thing is really the newest queen position X, and this thing is its position in Y. We know this is correct. We tested that earlier. That should be correct as well. I can't... hang on. We're doing -1 here. That means this isn't... okay. Here's a better idea. That's the number of complete columns. The number of complete columns -1 is the newest queen position X, right? So we're basically taking this number and making it 0 indexed, and that is actually the position in X. We can replace that with it as well. And then I think if we use that here, I think that's what the problem is. I think it was comparing, yep, there we go. It was comparing non-0 indexed with 0 indexed. So it was an out by 1. Okay, implement diagonal checks. And I think because we use abs here, there probably aren't any problems, but let's just check our test coverage. So given, let's say, bar diagonally adjacent queens should return invalid. I just realized I'm talking about abs, so I'm not really like explained. If anyone isn't clear on that, it's just short for absolute. So it's getting the absolute difference, so you won't get minus numbers with these subtractions. Now let's see, how can we set up a... Setting up a bar diagonal example is actually a little bit difficult because it's tough to do it without also causing a different type of conflict. I'd like to put it there, but then if I put that there, either of the other places I can put this one will hit a nearby diagonal. So, here's a really silly way to do it. We can do this. Because we only ever check the validity of the latest entry, it doesn't actually matter if these two are conflicting, for the sake of our test anyway. It's a bit weird. We're kind of abusing the invariance of a function. If you remember, I was talking earlier about the invariant being that the earlier ones are always valid. Well, actually, I was talking about invariant, not having a none here, but similarly, an invariant of a function is that the earlier queens are all valid. So we're kind of breaking that invariant for the sake of this test. Yeah, it's probably fine. It's just a bit weird, but such is life. 0, 0, and that's a 2, is it? Yeah, 2. Okay, so we want this to return false because it's invalid, and I think that will probably, yep, that passes first time. Now we also want to check for diagonals in the opposite direction, so that's given what, reverse diagonally adjacent queens should return invalid, and that would be something like, actually let's just use the same thing. I don't know why I'm copying it. So what do I even mean by reverse? Because you're always checking the latest one. I guess the only other diagonal case to check is an instance where it's below instead of above, like this. 2, 2, 0. Is that an exact inverse of, yeah, it is. An exact inverse of our previous test case. Oops. So we can just take this and do 2, 2, 0. So we basically just flip that around to check that it works both ways. Cool. Okay. Improve test coverage of valid check. Okay. So where does that leave us? I think that gives us everything we need just about. I think we're into the interesting bit now with the search. We have a validity function. We have the ability to serialize. We have our types. Now we need to actually populate the frontier and do the search. So that's pretty cool. Populating the frontier is dead simple. That just means creating these things, right? We just need to create these for, but keep in mind that, or these for, sorry. But keep in mind we have to do it for any size of board n. So we have to do for, let's say for I, no, because it's for row. Yeah, for row in n and 0n. Create a new board, and it's gonna have to be. We can do something like 0 to n dot iter dot map. Value we don't care about, none. So that would give us a board of nuns. And then we can set the first one to some row. That should give us one of each board for each possible row you could set the first column to. And again, these are all going to be valid to begin with, so we don't need to check validity here. Then we can add those to our frontier. That needs to be mutable. I don't know why I wasn't complaining here. It probably should have been complaining. Does it not need to be mutable to do that? Yeah, of course it does, right? Oh, sorry, I've not collected it. And then, yeah, cannot index into... Oh, well, because it still thinks it should be a vec of usize. Well, actually, no, it needs to be a vec of option usize. Really doesn't like it. I really thought it would just, the collect would figure its life out and say, okay, this has become a vec. What am I missing here? It's getting a range of I32. Oh, is it? A method named iter struct range and government scope. Wait, can you not iterate a range? Am I going crazy? You got into iter instead. Can I? Oh, you can just map over it directly. I didn't need the iter. Okay. There we go. Okay. So we've got our board. Oh, I'm just realizing we haven't got a failing test. I should probably unignore this test here. So we're now getting this. Actually, I might also add a more interesting test. I guess that gives us 2 failing tests at the same time, but the N2 example is just so boring, right? It's nothing happens, it fails, yay, like whatever. Let's have a test that's actually doing something cool. So given N4 should return 2 solutions. Net result equals N queens 4. Net expected. No, we don't need to do that this time. We just need to do that equals result vec bang, vec bang, vec bang, and then put the correct values in here. And those correct values are going to come from here. And here. Does that compile correctly? Yeah, cool. We've got 2 failing tests. All right, and those should start passing as soon as we have the search working correctly. Okay, so we're now able to populate a frontier. We want to perform our search. We've got our validity function. We've got the ability to serialize it, but we do need to actually perform that serialization. So, what's the actual name of the serialize function? What did I call it? Oh, it's literally just serialize. Okay. Serialize. Wait, how are we going to do this? So serialize takes a single board and it doesn't have the option. So let's say that every result we add to this results collection is a complete board. Let's just take that as an invariant and assume that's always the case, and we can just enforce that when we're pushing to the board. In which case we can say results dot iter. Get that. That always happens. That shortcut is so annoying. Iter map and vec option usize. We just want to get rid of the option. I think what we actually want is a filter map. Wait, no, it's double. It's nested, isn't it? It's a 2-dimensional array. So we want to map over it first. And then within this map, we want to say, okay, so that will give us a column. And that column will contain, what was that? No, sorry, it's not a column, it's a board. And that board will contain columns that may or may not be actually there, maybe options. So we want to filter. In fact, we could just map unwrap, couldn't we, I suppose? Iter map and column dot unwrap. And is that, what's that going to give us? Well, I think that's going to give us I think it's going to give us a vec usize. We've basically just removed the option. So then we should be able to do board, serialize board, and finally collect to return it. No way. I was about to say, no way. Did that just work first time? Of course it didn't. It doesn't like the serialize function. I think it might be getting confused. I've given it the same name as file, which is of course the same name as the module. And I wonder if I did that, would it? Yeah, now it's seeing the actual thing. Let's just rename this to serialize board. Why didn't that work? That was weird. Yes, because it didn't work. try from here. Serialize board. Yeah, it just doesn't work over here for some reason. Well, just do that manually, and yeah. Oh, it's not actually a public function. Here we go. Do I need to do the same here? Yeah. I kind of assumed IntelliJ would make it public when I extracted it from the file. So expected. Oh yes, of course. Yep, that needs to be a reference. Expected reference of vacuum size. Got map. It's a map. Where's the map coming from? So it's a map of iter. Goodness, why is it a map of iter? Oh, hang on. I'm not. I need to collect it inside here as well, don't I? Okay, there we go. So didn't quite work first time, but we have something neat here now that will iterate through our results, get rid of the options, wrapping them, and then serialize them to a string and return the vec. We've also populated our frontier, so on both those fronts we're ready to go, and we just need to actually perform the search, which is the fun algorithmic part. So let's say while frontier is not empty, so long as we have things to check, we want to be checking them, and we want to get the board from the end of the frontier. So pop is going to actually remove a board from the frontier and give it to us to play with. And then we're going to want to say, okay, let me think about this actually. Let me plan this out. We're going to want to say, is it valid? Is it complete? No, I think the way to do it is, if it is valid and complete, add it to the result. If it is valid and not complete, add it to the frontier. So if you go back to our example, we're basically saying, if you get a board like this that is valid but it is incomplete, then we want to add it back to the frontier so that it can be looked at again to generate more of these. And if you get a board here that is complete and valid, then we want to add it as a result. I'm missing something. I'm missing the actual iteration, the generation of new boards. So, okay, yeah. So I've skipped ahead too far, basically. What we need to do first is generate for new boards of a current one. Then for each new board, if it is valid and complete, add it to results. If it is valid and not complete, add it to the frontier. And then if it's invalid, we just do nothing, right? We just leave it. So let's start with generating those 4 new boards. So for, let's say Y, oh, we used row up there. Let's just stick to the same convention, say row. For row in 0 to n, let's let new board equals board.clone. So generating a new board, and then we're going to say we need to know what the latest doohickey is. Basically, we need the same bit of code we had in validity over here to get a number of complete columns. And that's going to be something like this. We can also reuse that when doing our check of whether it's complete. So we're going to say board iter filter down to if it's sum and count. So yep, that looks valid. Now we want to say that won't be 0 indexed. So we want to say number of complete columns -1. So get the latest column and assign it to a row value we're looking at. So we're creating for each row a new board that sets the value of that queen to be, you know, sitting in that row. And that gets us our new board, I suppose, right? I don't think there's anything else we need to do there. Now we need to check if it's valid. So if is valid board, new board. Expected vec option U size found. Oh, okay. Yep. So we actually need to. Hang on. Wait, where's the option coming from? The board itself. Ah, yes, of course. Yep. So I forgot to unwrap this up here. So we were getting an optional value back from pop. We don't need to worry about that. We can unwrap here because we are guaranteed it's empty. I have been using unwrap a lot, you might have noticed, but in every case that I've used it, feel free to correct me if I'm wrong, in every case that I've used it, it's in a case where it is guaranteed to be correct unless some invariant of a function is being broken. So these are all cases where actually we know for sure, even though the compiler doesn't, we know for sure that the value is going to be there and an error is not going to occur, like in this instance where we just checked that the frontier is not empty. So we know there's a value there we can pop. There's no need to worry about options here. So I guess it's to this point, okay, we can test if the board is valid, and then we want to say, okay, is it complete? And that's dead simple to do. We can just say, is the number of complete columns equal to n? And that's not zero index, so that should be correct. So if it is equal to n, then we can say results push new board to update our results. Results is not mutable. I always forget and then add it later. Need to get used to actually adding them to begin with. Use of moved value. Ooh, that's exciting. Yeah, that should be a reference. Did we not add it as a reference in here? Nope. And that's going to need us to fix the tests. That's one fun thing about inside out TDD and Rust. Got to be careful of your method signatures because if you get them wrong, you're gonna have to fix them in a bunch of places when you realize it's wrong. It's complaining about cannot borrow new board as mutable. Oh, did I not make it mutable? Okay, cool. So we add it to results if it's complete. Else, if it isn't complete, then we want to add it to the frontier. Boom. There we go. That was N Queens, and it is really cool to see it passing. Implement search function. So let's just add, well, I don't really have any other test cases. It's kind of difficult to generate test cases because once you get into the bigger numbers, there's a whole lot of solutions. Let's look up a quick solution to this problem is traditionally called the 8 queens puzzle. So there should be more than a few registered problems, solutions for 8 queens. Apparently there are 12 solutions when n equals 8. Let's do something really easy to quickly test this. Let's say let's my test. It's not actually commit this. Isn't a serious test. Let's just do a little experiment to see if everything looks roughly right. So equals result bang, just to see in the debug window what we actually get out for 8. Oh right, yeah, it's going to complain about that. Expected. No. What are you doing? You're saying blank is coming back for 8? No way. I thought we had it. Why? Have I hard-coded number 4 somewhere? Why is 8 not working? 8 is definitely a solvable size for the board. Drat. Vec string, vec bang. We're saying we expect it to be blank. Just check if this test is valid. No, it's not. It's not. It's not a working test. What's wrong with the test? Is it not? Oh, I see. Okay. It's getting stuck in a loop. It's not obvious when you're doing a test watch. It's more obvious if it's because I was using a test watch. It isn't really visually obvious. But if you run a test normally, yeah, now it's clear, because what should be happening is that it should be exiting out and showing us back into the terminal. But what's actually happening is that it's running our N1, which is passing, and then it looks like both N2 and N4 are getting stuck in recursive loops, which is, a pretty common problem when it comes to search algorithms. Easy bug to hit if you're not careful. So we need to debug why this is. Frontier is empty. They're definitely popping. Yep. So we're removing the frontier. The frontier is shrinking over time, and then we're adding to it with this new board. Is this check? This is the most likely culprit. If we're just never adding things to the right place and we just keep adding them to the frontier, that could cause it. So number of complete columns is not 0 indexed. N is also not 0 indexed. That looks like it should be happening correctly. Let's take a look what's going on here. Heading to results. Well, I guess I don't need that because it's going to be obvious whether it would do that or not. Oh, right, yeah, it's also not going to, yeah, recapture. So we're getting 2, 4, 2, 4, 2, 4, 2. So it is actually hitting. Wait. Complete columns is always 1. Complete columns is always 1. Why? If a frontier is empty, pop the board. Get the number of complete columns. Oh, wait. -1 is going to be 0. We're just always updating the first queen. We're not updating the later queens. Is this actually 0 indexed? We're counting the number of sums. It shouldn't be, should it? But in this case, yes. We don't want to just add to. Yeah. It's this line. This is the problem, or at least a problem. I don't know if there might be more problems. It's kind of awkward because readably, it's not super clear what's going on, but it probably will work. Okay, at least solved the recursive issue anyway. Remember earlier when I was like, "Hey, it worked first time." Ta-da! How naive. How optimistic. Number of complete columns is... Oh, it's just bugging me. This isn't a very readable name for this variable now. It's going to look a bit weird. I'm going to do something real quick. Index of latest of most recently added. Most recently added is way too long. The latest queen. That just feels much clearer to me. We're saying like this was the most recent index, and we're adding 1 to it, so we're looking at the next index. Makes sense. Okay, so what's going wrong now? Oh, it's panicking. The len is 4, but the index is 4. When it's getting to where? It's getting to 1, 2, 3. It gets into the 4th column. In which case, number of complete columns is going to be 4. And then, why does that cause a problem? Yes, okay. I think I see the issue. We're relying on number of complete columns over here, but actually we've added, after doing this, we've added another complete column. So the number of complete columns is actually +1. Okay, beautiful. Now we've just got the edge case. With N1, it's failing again because it likes to do that. And you know what? The easiest option might be just to say if n equals 1. If n equals 1, do something different. If frontier is not empty for row is valid board. It'd be nice if there were a neat way of doing this. So what's going to happen here? We're going to create one single entry in the frontier at position 0 because, yeah, there's only one. And then we're going to say frontier isn't empty. We're going to pop it, get the board, and then try to generate a new thing. It's going to go wrong here, presumably, right? Line 26. Yeah, line 26. If n does not equal 1. I'm not sure that's really the neatest way to solve it. I really don't like that I've now got loads of nesting here, but it'll... Oh, wait, hang on. That's not solved. It's not even solved it. Given n1 should... Oh, okay. So now it's not actually returning... Right, yep. That's not going to work either. But now it's just returning a blank instead of a 1 entry with the 1 queen. It's always the edge cases. And also all the other cases. Result, push, new board. Tell you what, actually, maybe that solution is viable. Let me just say else result start push board. Yeah, that works. Okay, so fix recursive loop in search. Now let's do what we were trying to do before and just do a quick test to see what would it look like if we passed 8. We should expect 12 results back. That's not an easy output to read, is it? Let's say, oh yeah, tell you what, let's actually just do results.len 12. Oh, 92. That is a few more than 12. Well, at least we have it passing for 4. Why is it finding 92 solutions? Curious. All fundamental solutions. I think this list on Wikipedia is only the number of solutions that don't have in flipped versions and variants and all sorts. Oh, here we go. The total number of solutions is 11 times 8 because every solution has 8 variants and the total number is 92, which is exactly the number we have. Boom. Yep. Okay. We've definitely properly kicked N-Queen's butt. I can't be bothered to write a test that has 92 different boards like this though, so I think we'll call it quits there, especially as this has turned into a longer Screenkata already. But I hope it was interesting to go through a more complex, more algorithmic problem. There's a few bits of cleaning up here. Again, I won't go into them for the sake of time. There are a few things that you could improve here. Like all these tests are very, very similar. They should really be parameterized tests because there's just lots of duplication between them. Same again with the acceptance tests. You could easily do that with a macro. I think I'm mostly happy with this valid board function. If you wanted to do it more optimally, of course, if you really wanted to hit the performance, you could replace the data types up here with bitwise, with bitboards, using bitwise operators, and you'd probably be able to just replace. Actually, I think this entire thing. You could probably do something like that, and that would be valid. You could just use a single integer instead of, n integers. And that's obviously going to reduce your memory footprint, but it'll also drastically reduce your number of allocations. And the allocations are a real thing that is going to save you lots of time and improve your performance a lot. Other improvements you could possibly make, for the sake of readability, it would be nice to reduce this nesting, which you can quite easily do by just extracting this to actually a separate method. I doubt IntelliJ will do it correctly first time. It's probably not going to pass, but oh no, it did. Nice. But then this becomes a little bit more readable, a little bit less nested, I think. And then similarly, populating the frontier is just like such a minor concern. Don't really need that level of detail in this function. Keep the high level of abstraction areas separate from low level abstraction areas. Yeah, there's a few things you can improve, but hey, we have implemented N-Queens and done it all in Rust using TDD. I think it's really interesting to see how outside in TDD just would not have worked for this problem, right? All that work we've done, which we had lots of tests to help us drive it, and every step of the way we had great confidence in what we were doing because we could always go back to the tests and see which things were in there and which things weren't and so forth. All those tests were there for us and helping us step by step all of the way. if we'd just done pure outside in and tried to drive this sort of from the outside as treating it as a black box, then you would have had like 3 tests, right? And in fact, this one, we had both of these failing at the same time. So you would have basically implemented the entire thing in one step. So these sort of this inside out approach was really, really valuable. Yeah, that's TDDing a search problem in Rust. Thank you for watching. And we'll probably make some more Rust screen cutters soon. Bye bye.